In today's lesson, we're going to be focusing on exponential functions again, but this time instead of working with exponential growth functions, we're going to work with exponential decay functions. So instead of seeing a rising curve, we're going to see a declining curve in our exponential growth function. So let's just take a couple look at some of the specifics between the differences between the two. If you recall, our original exponential function was a times b to the x power. And each of these parts has a specific component now that needs to be looked at. Most specifically, the b unit is going to be extremely important in us determining what we're dealing with. So you can see here, if the b is greater than 1, we're dealing with an exponential growth function. And now we're adding exponential decay, and so you can see that the difference here is that the b value is going to be between 0 and 1. So that is going to actually give us an exponential decay function. So what I'd like to do is maybe look at that a little bit closer. We can kind of compare them, if you will. So we'll start here. So we'll just say that they all have a times b to the x, and we know that a is going to be greater than 1. So if we look at growth, looking at the growth function, we know that the b is going to be greater than 1 as well. And what that's going to create is a situation where we have an asymptote, and our graph is going to hover just above that asymptote, and it's going to slowly curve up as we go from left to right. So that's what the exponential growth function is going to look like. Now, if we're looking at an exponential decay function, the b is going to actually be between 0 and 1. And again, the asymptote is going to be treated exactly the same way. It's going to be treated as a barrier that the graph cannot go beneath. But this time, it's going to be a graph that declines toward the asymptote in a curved manner. So you can see the difference there. Now, in general, what you're going to see here is that since b is between 0 and 1, you're going to be dealing with fractions. So b is probably going to equal a fraction, but you got to be very careful, because let's say b, in this case, and I'll give you a more specific example. Let's say we have y equals to 2 times 3 halves to the x power. If you're specifically looking for fractions and automatically assuming it's a decay function, you can get into a little bit of trouble here, because if we look at this, 3 halves actually is greater than 1, so this is a growth function. So we're going to have to just be very careful not to use fractions as our general go-to as determining whether something is a decay function or not. Just be sure that you look at the decay function, or look at the fraction a little bit more clearly to determine whether it is actually between 0 and 1. So let's go back to the original set of notes, and we can look at some identification problems. So if you look at sample problem number 1, these are just basic identification problems. We want you to just state whether we're dealing with growth or decay. So you need to look at A, B, and C for sample problem 1. And just take a second to see if you can identify what type of exponential function we're dealing with. Okay, so here we have 3, and we've given you some intentionally, I won't say tricky ones, but some that you have to look at a little more closely just so that you know what you're dealing with. So we're always looking at the b value. So in part A, we're dealing with a b value of 2/3. So since 2/3 is between 0 and 1, we can say that this is an exponential decay function. So that's pretty straightforward. We have a times b to the x power, and our b value is a fraction between 0 and 1. However, on part B, our b value is a fraction, but this time 3/2 is bigger than 1. So this is representative of a exponential growth function. And lastly, c, we've got to be real careful here, because if we look at the b value, it looks like 3 is actually a b value. But in reality, that 3 does not represent the b value, because if you think about it, an exponential growth function has to be to a positive, an exponential function has to be to a positive exponent, so y equals a times b to the x. And we can see here that the exponential, the exponent is actually negative, so we actually need to rewrite this. And so we can use f of x, or we can use y. We're going to get 10, and of course, to make this positive, all we need to do is to rewrite the 3 as a fraction, and that makes it a positive exponent. Now that we have a positive exponent, we can simply look at the b value here, and we can see that it is a fraction between 0 and 1, and so this is a exponential decay function. So this first sample problem is a good opportunity for you to see different ways that exponential functions could end up being written, and quickly determining whether it's a growth function or a decay function. Now, the remainder of this section is going to focus on decay and graphing decay functions and decay models. Now, if we look at this first little sample here, graphing the decay function is the same as graphing a growth function. We're still going to use a t-chart. We still have to know about the asymptote, so it's very important that you know about the asymptote, and that it creates a barrier which the graph cannot go through. And you can see through creating a t-chart that we're going to have this declining graph. So you can see that the graph, when you go through the points that we plotted through a t-chart, we have this declining function. So graphing these is very similar to graphing the exponential growth function. Now, I would like to point out one more thing. If you recall that the y intercept is going to be represented by the a value in general. So you can see here that it passes through the point 0a, that is the y-intercept, and then in this case the x-axis is still the asymptote. So a couple quick little shortcuts to helping us graph this a little bit quicker. So let's take a look at a sample problem here. Let's look at a first example. We can first of all see that we have a b value that is between 0 and 1, so we know we're dealing with decay, which means that we'll know that the general shape of our graph will look like that. The easiest way to get started on this is to quickly draw our y-intercept, which is going to be a result of the a value, so 0, 3, and then we would simply t-chart a couple of other simple points. So we've already done the y, and so probably the better things to do would be the negative, we've already done the 0, so we would probably want to do the -1 and the 1 in this case. And then plot each of those points in for x values, and then we'd come up with the corresponding y, and then graph the exponential decay function. So let's use that knowledge that we learned in the previous section of growth functions and now apply it to the decay function. So go ahead and sample problem number 2. Pause the video and let's see if we can graph the exponential decay function here. Okay, so the first thing I want to identify, and even though I know we're working with decay functions here, you still want to get in the habit of recognizing that that is going to give us a decay function. Secondly, that value right there is going to give us our y-intercept. So I can quickly plot 0, 4, and I know that's where it's going to cross the y-axis. So now I just need to t-chart a couple of extra points, and I'm just going to do the -1 value and the +1 value here. And if we look at the -1 value, let's just go ahead and plug that in. That's 4 times 2/5 to the -1 value. Anytime we have a negative exponent, we want to flip the fraction. So that gives us the 5/2 power to the first 5/2 to the first power, and of course there's no need to write the first power. And then we'll simply multiply these two together. So 4 times 5 is 20, 20 divided by 2 is 10, and you can see that we're going to get -110. And of course, in this particular coordinate plane, you got 7, 8, 9, 10, so we're going to be somewhere up here at -110. Kind of not a real nice point, but it gives us a general idea of where the graph is coming from. So now if we look at the next point that we want to graph, the 1 value, we get 2/5 to the first power, which is just simply 2/5. So we're going to multiply 2/5 times 4, which is going to give us 8/5. 8/5 is the same as 1 3/5. And of course, anytime we get a fractional unit, we're just going to guesstimate that as best we can. So we're going to go over 1 and then up 1 3/5, which is just somewhere between the 1 and the 2. Now at this point we could graph the 2 if we wanted to, and that would require us some math, but we pretty much have a sense of how this thing is going to decline. Now when we get to here, we know that that x-axis is an asymptote, so we're just going to do the best job we can to curve that off and not touch the x-axis. And that in general gives us our decay function. Now when graphing growth and decay functions on a test, it's very important that you give me these 3 points that we've plotted here. This is very similar to parabolas where the curves are not always exact when we draw them, so we want to make sure that we label everything properly so that it's easy for grading, and we know that we can represent that we are doing this correctly. So let's look at our next example. If you recall back from the growth model notes, we had again the h and the k values that created some shifting. So the h, if you recall, sent the graph to the left or to the right, and then of course the k sent us up or down. Now don't forget that the k also shifts the asymptote up or down as well, so we need to make sure that we take care of that. Now we have sample problem 3 here where we're going to graph a decay function. We know it's decay based off that b value, but this has a shifting component, so you can do this one or two ways. You could graph y equals 3 times 1/2 to the x power, then shift the graph accordingly. Or, if you like, you could simply t-chart the entire thing, whichever way you feel most comfortable with. So go ahead and pause the video right now, and based off your experience, which one you like best, go ahead and try to graph the new decay function since it's being shifted. Okay. You can see here, if we look at the h and we look at the k, if you remember, the h is always opposite of whatever its sign is. So in this case we have a +1, so that we're going to actually go the opposite of that. We're going to shift any graph that we do 1 to the left, and then we're going to shift 2 down. Now that's assuming we graph the base graph here. If you t-charted the whole thing by itself without doing the base part of it first, then your shifting is going to be taken care of in your mathematical calculation, so you don't shift it twice. So I'm just going to graph this base function right here, and so if I just t-chart a couple of points, negative 1 and 1. And you can do the math on these. That's going to give me negative 1, 6, and 1, 3/2. And I'm only graphing this function right here, right now. So I'm going to just kind of do 0, 1, 0, 3. So that's my y-intercept. And then negative 1, 1, 2, 3, 4, 5, 6. And then 1 and 3/2, which is 1.5. Now, basically what I get here is I kind of get this exponential function that looks like this. But that is not the exponential function that I'm trying to graph right now. What I'm trying to do is I'm trying to graph the whole thing. So based off this first base graph, what I need to do is I need to shift every single point that I have 1 to the left and down 2. So I'm going to take this one to the left and down 2, and I'm going to get a new point. I'm going to go 1 to the left, down 2, I'm going to get a new point. I'm going to go 1 to the left and down 2 and get a new point. Now it's very important also that we shift our asymptote down 2. So instead of at x, our new asymptote is going to be at the 2, or at the negative 2 in this case. And so now I have new points, and I can graph through those points as best I can and then curve it off on our new asymptote. So the actual answer in this problem is the blue graph. So this is the answer that we're looking for here. The red graph is just a guide to help us with our shifting component. Alright, that's a good little overview of graphing exponential decay functions. You'll definitely need to know the difference between growth and decay and how each of them are graphed and how a graph is affected by shifting. Alright.